working. Got it. All right. So let's go over the exam questions quickly. Here's the function count occurrences. So it gets a vector v and an integer k. How many times does k occur in v? Do you want me to do this one or skip it? Do it? Couple do it's. Now these problems, problems similar to these will appear on the final. So you're going to start thinking about that. So this is a good exam to practice for the final. So count occurrences. And so it takes a vector of int v and an integer k. And this, I don't know if I did this or not. It doesn't matter for this problem, but normally that would be a constant reference because you don't need to make a copy when the function is called. And you don't need to modify v, so you can make it const. So like most of these problems, we need a loop that goes through the vector. And the size information is available through the size function on that vector object that we have. Each time we find a k, we're going to increment this count. And then at the end of the function, we'll return count. Because we need to initialize count. So start with 0 occurrences of k, and each time we find a k, we increment count. And then at the end of the function, we return count. And the return value is int here. So we're returning an int. So what about number 2? The max value. The maximum value of an array A of length len. Once again, we need the loop. It's very similar to the code we just looked at. Look how similar it is. Instead of count, we're looking for the max value. And at the end of the process, we'll return max. And we're not going to increment max. We're looking for, when we find a new maximum value in the vector or the array, we set it to that. So if A of I is bigger than our current record for max, then change max here. But we don't want to start at 0. We want to start at A of 0. Just in case the A contains only negative numbers. If we set it to a 0, the max will end up being a 0, even though it's not truly the maximum value in the array, if the array is all negative numbers. So that's how to do that one. Look at the similarity between these, very similar. And linear search. Find K and V. It's going to be very similar to these as well. Let's see what it looks like. If we don't find it, we return -1. If we find it, we don't need this. If we find it in the loop, if v of I equals k, then we found it at I. Look how similar all of these are. They're all using a for loop. Oh, this is not correct. So we're not in a vector anymore. We have length being passed in as an argument there. What about the next one? Append vector. So we've got a vector v and another vector w. We want all the elements of w added to the end of v. Let's copy the code. Did you notice that when we declared this, the w is const, but v is not, because we're going to modify v. So we cannot declare it as const. But w, we're only reading from w. So basically, each value we find in w will append onto v. So I'm going to scan through w, and for each value we find, this is w of I. For each w of I, we want to push it back onto v. And then we don't need a return statement. If we want to, we could put that in there. It's a void function, so we could just do that. But this return at the end of the function is an implied return. So this is okay, the compiler accepts that. But there's no reason to do it, it's implied. At the end of the function, we're going to return.
We don't need an ampersand when we have const.
Need a what?
The ampersand, we don't need it if we have the const, because we're not changing anything. Do we need because the constant
Oh, this here?
Yeah.
No, it'll make a copy. This will make a copy of w. The copy cannot be changed. But this is expensive. This is wasteful because it makes a copy. This just says the copy can't be changed. I would have to verify that, but I'm pretty sure that's what it means. This says, don't give me a copy. Give me a reference to the thing.
The reference is in case you want to change the original, right?
Yeah.
That's why.
Yeah, no. If you want to change the original, you don't use const, and you use a ref. You have to use both. No reference and no constant. So both of those are at play there. And if you're reading from it, but you don't need to change it, then you should declare it as a reference so that you're not wasteful in the sense that you don't want a copy being made. It'll still run. I mean, that runs. All right, append vector. And then is all positive. So we're going to need two loops here because we have a two-dimensional array. We'll go rows and columns. Well, we could go I and j as well. I'll do I and j this time. First, we'll do the rows first. Well, we'll do the rows in the outer loop. So for each row, we scan through all the columns. So here's the trick. We won't know they're all positive until we finish checking each item, right? You can't say they're all positive if you just look at, the first row. So it isn't until you exit this loop that you know that they're all positive. So what you can do inside this nested loop is to look for something that's not positive. If it's less than or equal to 0, if you found a number less than or equal to 0, you know that at this point, not all the values are positive. So we can return false right there. And my sort, I think I'm going to skip that one. That one's pretty simple, and you either had it memorized or you didn't. Okay. Is there anyone who wants me to talk about my sort? Okay. Min value. This one here. See, this code has an error in it. Your job is to write test code that exposes the error. Write test code that exposes the error. So the test code needs to fail, right? In a sense, it needs to terminate the program. And let's use the assert function to do this. And the problem is we're initializing smallest to 0. But what if if all of the values in the array are larger than 0, then the smallest will be larger than 0. So this is a logic error. So the job is not to fix the code. The job is to write a test that will fail to expose the bug. And this is how it's recommended to be done in practice. This is how if you're on a team that's writing test code, this is the approach. You don't, when you see this bug, you don't just fix it. You write a test. They'll fail to expose the bug. If you haven't discovered the bug at runtime already and you notice it in code, I guess it's your choice. Do you write a test to expose the bug first and then fix it, or just fix it? I think a purist, test-driven approach would fix the bug. Would write the test code to fail, fix the bug, watch the test to succeed. That would be the process. So we create an array A with numbers. I'm going to give you a minimal example. There's our array. It only has one number in it. So we call min value, pass in A, comma, size of A, which is 1. The minimum value of that array should be 1, right? But it's not. That will fail because we're going to end up returning 0. See, when we get to A of 0 will be 1. 1 is not less than 0. So we do not change smallest. We leave smallest equal to 0. And then we end up returning 0. And so the test, this assertion will fail. So we say that the test code succeeds in the sense that it exposes the error. Okay. Any questions on that one? Is lucky. So the vector v is lucky, and I should have done this, by the way. I didn't. This is but it doesn't matter for the problem, it doesn't matter. So you're making a copy of v, but we don't need a copy. So if v contains a number that's evenly divisible by 7, we say that v is lucky. So we'll return true in that case. So we're going to want one of these loops up here. So let's range through all of the indices in V, and we're going to look for a number at I, which is evenly divisible by 7. That means if we divide by 7 and look at the remainder should be 0. We found one. If we found one value in V evenly divisible by 7, we return true. Otherwise, we'll return false. But it wasn't very big. Any questions on that one? Oh. Suppose your home directory contains a folder named Sam. All right. This is the home directory here. Here's the home directory. Oh no, that's not the home directory. Sorry. So, there's the home directory. /home/Ubuntu. I have 2 folders in there. Let's suppose it contains a folder named Sam. I'll just make that folder. So there's a folder named Sam in the home directory. And in this folder, there's a file named hello.cpp. There it is. Show the Unix command to move hello.cpp into the home directory. I'll make no assumptions about your current directory, so we could be anywhere. In fact, let's go into the workspace and let's go into this point folder in the workspace. So where's somewhere else? We want there's a folder in the home directory named temp. See it? Sorry, Sam. And inside Sam, there's a file named hello.cpp. There it is. So I can see that from where I am. I'm at this location in the file system. That's the path to my current directory. And Sam is on another branch. You know, Sam and Workspace are sibling folders. So that the task is to move hello.cpp into the home directory. So it's move ~sam/hello.cpp. That's the path to the file hello.cpp. Now that path works anywhere. It doesn't matter where we are in the file system, because I'm using a tilde there. So this is called an absolute path. I'm telling the system how to get there. It doesn't depend on where I am right now. So I could be anywhere, and this path will resolve to the same file. So I'm going to move this to the home directory. So you could do it like that, or just like that. So this is the move the source to the destination. I hit enter. It moved it. Let's prove it to ourselves. If we look in the home folder, we see hello.cpp. If we look inside SAM, we see nothing. We moved it out of SAM and into the home folder. What about 10? Suppose the file a.out is in the parent directory of your current directory. Show the Unix command to delete this file. Oops. So if I look in my parent directory, oh, there is no a.out, is there? So I'm going to make one. Oh, I can't because it's cracked. Oh. I don't know what happened to my files. Just create a fake one. There's a.out. We'll go into this point folder. Okay, now let's look at it. It doesn't matter what's in our current folder. If you look up into the parent, there's that file a.out. Okay, so that's the problem. Suppose that file a.out is in the parent directory of your current directory. That's what we have. Show the command to delete it. So it's rm .. /a.out. We go up to, that's a path. It's the path to the parent folder followed by a slash, followed by the name of the file, and that takes it out. If we look at the parent, it's no longer there. What about 11? Suppose you have a file named main.cpp in your home directory. Well, let's do that. Let's create that. So I'm just going to go cd enter. That goes to my home folder, by the way. I could also do cd tilde. That's the same thing. So just cd by itself puts you in your home folder. I have hello.cpp right there. And it says that it should be main.cpp. So let me just rename it. So we have main.cpp in the home folder. Show the Unix command to create a copy of this file named test.cpp. The copy should go into your current directory. Make no assumptions about where your current directory is. So if we were inside workspace and inside point, we want to make a copy of main.cpp into my current location. Well, main.cpp is in the home folder, so it's ~/main.cpp. The current location is dot. The current folder is dot. Oh, we could do this. What did I have to name it to? Test. But this is this is implied. If we just do that, it works fine. There it is, test.cpp got created. Suppose there's a folder named lab01 in your parent directory. Show the Unix command to create a folder named test within the lab01 folder. Suppose my parent has a lab01 folder. Well, we better make that just to illustrate how it's done. But it's in the parent, so I need .. So if I look up into the parent, I see the folder lab01. And what we need to do is create a folder called test inside of the lab01 folder. So we're going to make a directory called test in the lab01 folder. So we have to go up to the parent, into lab01, and then create the test directory like that. Once again, we look in the parent, there's a lab01. And we look inside that lab01 folder, there's the test directory. Now I'll delete it. I don't need any of those. So these will come on the final as well. So practice these commands. And the job is to do all of these in a single command. That's why I show the Unix command. Just one command to do it. The skill here that a lot of you are missing is how to specify a path name. So these commands operate on path names. And that's what you need to practice. All right. Binary search. I don't think we need to do this. This is done. And that's it. Any questions? All right. So we're working on classes right now. And we don't have class. That's an unintended pun. We don't have class on Monday, right? Monday's a holiday, okay. We covered this already, didn't we? Yeah. And so now this is also application development, this lab here. And the lab is to implement tic-tac-toe and then do some extra credit here. Do you want to review classes, or do you want to start talking about how to solve the tic-tac-toe problem? How many people want to review classes? I think that's what we'll do then. All right, let's review classes. So last time we looked at this this point class, right? And let's do another one. Let's take it. Let's see if we can look at here. So we have a rectangle class, a number class, here's a number class. Let's do this this final exam type problem here, okay? We need to implement this, this number class. Remember, a class is a data type, so we're going to create instances of this data type. Let's do this. Let's go into here. Let's see if that runs. Looks good. So we have the following class to implement and test. Now on the exam, you'll be given problems that look like this. So questions. Provide the implementation of the constructor. Provide an implementation of the set value function, the isPrime function. Provide test code for the isPrime function. Let's try this. So we'll have this number class. So we're going to create instances. I'll say number n. So we create an instance of n, and we want it to be, say, a 7. We want this number to represent 7s. So you're going to pass in this argument 7. So the constructor, see this second section is where the member variables are. The first section is the name of the data type, the name of the class. The third section are the member functions. And there's one function that's called a constructor. And you can have multiple constructors, by the way, but we only have one here. You can also omit the constructor. The compiler will generate a default constructor for you if you do that. But if you define a constructor, which we'll do here, the compiler will not generate that default constructor. The constructor, you can tell it's a constructor because the name of the function, the name of the constructor function, is the same as the name of the class, the number. Capitalization is important there, it's uppercase N. This constructor function is declared as taking an integer value. We simply take that value that's passed into the constructor and initialize our member variable n to it. So the purpose of the constructor is to initialize instances of this data type. So once we invoke the constructor here, we're creating an instance of the number data type, and we refer to that instance with the name n. We can call functions on it. So n should be prime. So if we pass in a 7 to this number class, we want the number to represent 7s, or 7. So when we call isPrime on n, we use the dot notation there. So this is this n. That's the instance. They talk about this as being the implied argument to the function isPrime. So what you can see when you see this here, what you can look at, what you can imagine, is that you have a function isPrime and you're passing n into it. See, so when you invoke the function through the dot operator on that variable that represents an instance of that class, it's like passing in this n is like what we call an implied parameter. But this is how we do it, right? Like this. All right. Now this won't compile because we didn't define the class yet. Let's do that. So we do class number. Then there needs to be a semicolon there. It's kind of important. There's a public section. And this needs to have the constructor. And the constructor's job is to initialize the instance. And what's going on with this? See, this is, remember I was talking about implied data types. I'm sorry, implied parameters. So here you can think of it like this, that you have number, that this number here that's being passed in, that the n is the, let me look at it, let me try it like this. See if I've never tried this before. It'd be something like this. N is, we call the constructor, we pass in a 7. This is not valid syntax. I just want to illustrate this for you. Actually, that might work. That probably will work, but we're gonna make it fail. We're gonna make it fail here. And it's too hard to do here. I'm not gonna do it. See, the n here declared as an argument has scope. It exists only for the body of the function. When the function runs, this n comes into existence. It's assigned a 7 from this call here. And then the function body runs. There's only one statement in there. And when the function finishes running, then this n, this parameter argument n, is just simply discarded. That's its scope. It just exists for this one time when the function runs. But that n is used to initialize the instance. And so we have what's called an instance variable with the same name n. It's like two people in the class with the same name. Two different things, one name. So we need to be able to add a little information to tell the compiler which n we're talking about. And if we don't have any information, the compiler takes the n with the most constricted scope, which is the argument n. So if we want to refer to the member variable n, then we use this syntax here. Actually, this represents a pointer. It's called a C++ pointer. And this is how you dereference a pointer. This is how you use the pointer to access something inside the object that the pointer points to. Oh, and by the way, we need to declare that n. There's the member variable n. And I put it in this private section because it's normally kept private. See the minus sign here? That's just an indication in the UML diagram that we want this member variable to be hidden from the outside it should only be accessible to code that appears inside of the class functions. And these are set to public. They don't have to be. You can have a function that's private. That's fine. That's fine. You can have a member variable that's public. That's fine too. It's just not how we're doing this problem. Okay? In this problem, the member variable is private, and that's generally how it's normally done, is to make the member variables private, by the way. That's normally how you do it, by convention. That's called data hiding. So there's some benefit for a data type to hide its internal data to the outside. Just give it an interface, a minimal interface. All you need to do is call set value and is prime. That's it. You don't need to access n for any other purpose. So, so you're restricting what can be done to the data type. You want to. It's always good practice when you're coding to limit the scope of what can happen. If you open things up so you get more possibilities, then it's harder to analyze the behavior of your code. And you're always fixing it. So things are always broken all the time. So you want to keep things as narrowly scoped as possible. So now, coming back, we have an implementation for the constructor. So this line is okay, but this line here will not run, will not compile, because we didn't define as prime yet. Let's do that. So is prime, let's just return true for now. So remember this will let the compiler run. Oh, assert not declared. We're not going to use this here. What test passed? There we go. All right, let's go ahead and implement is prime. Rather than doing it here, I'm going to implement is prime outside the class. Is prime returns a bool. It's in the number class. That's how it looks. Actually, when we call is prime, we don't need to modify the member data. The state of the object won't change. So we can declare is prime as const. They have to match, by the way. Line 27 and 32, they have to match exactly. So if you call one const, you have to do the same thing on the other one. So our little algorithm for doing this is that we start at 2, and we go up to n. And if we find that, that n is divisible by I, then we know right there that it is not prime. And if we finish the loop and don't return, then we know it must be prime, because we didn't find a divisor. So that's our algorithm for finding prime numbers. You see the function, look at this n. You can think of that as the implied parameter here. Well, not exactly, that's not right. The class itself is an implied parameter. The instance itself is an implied parameter.
But what did he say that you call it? What did he call it, const?
Because the class, the class's state will not change as a result of executing the function. How do you change the state of the class? It means any member variable can change. So if is prime can change the value n,
Oh, okay. I thought I wouldn't let I change either. So it would let I change it.
we can change I. I is not part of the state of the class, of the instance. It's just a temporary variable that we use inside the function. So after we return from is prime, and the member variable n will not have changed. I'll show a little bit more about that. So this works. This code is good. You see, if we tried to modify n here, suppose we did that. But here we said, oh, compiler, is prime will not change the state of this instance. But n is part of that state. So this will fail to compile. Assignment of member n in read-only object. Well, we can modify I, because I is not, it's not a member of the number class. I is just a temporary variable that we brought into existence to execute the function. You think that's an important detail? It is. You know, a good programmer will be very careful to declare this. If you see an API, like someone gives you a library that you can call into, they're going to get their consts and references exactly right. So it becomes very important. If you're just a user of a library, maybe you can be a little sloppy, small program. No one's going to review your code. You get a little sloppy. You don't have to define things as const. You get away with it. But I wouldn't get into that habit. As if you interview for a job to do this kind of work, and you're being sloppy and leaving off const when you should declare things const, then that'll be noticed immediately. Unless your boss is a sloppy programmer, then you're going to get, then they won't notice. Okay. And anyway, that's that. What about this set value? Let's change the value of n to like 9. Now it should, when we call it is prime, it should return false. So we need to implement set value. And that's a void. Now we can't declare that const because we're going to modify n. It's the same as the constructor here, actually. So we don't want to create a new instance of n. We want to reuse, this n that we already have. We just want to change its internal value. So we define this function set value. I'm going to show you a little bit more here. Let's suppose, let's use the vector. And let's create a vector of number. Did I do this last time? Was it a vector of point? Did I do that?
You
Maybe
did a
not.
point last time.
Huh?
You did a point.
I did point, yeah, but did I do a vector of point? Maybe not. I want to show you that number. We've been doing vector int, right? It's vector of some data type, but we can also have a vector. So a vector is like a sequence or container, sequential container. So it can contain instances of the number class, just like it can contain instances of int or double. Let's create 10,000 numbers. By the way, what I'm doing here, I'm just trying to illustrate how to use vectors with number, but this is not the most efficient way to do this. So let's push back onto V an instance of the number class like this. So that's 10,000 sevens, right? Or 10,000 number instances that represent 7. But instead of 7, let's call rand, say mod, just rand. Maybe 10,000 is too many. Let me try 1,000. So now we have a vector with 1,000 random number instances. And let's call this function called count primes. I'll pass V in there, and then we're going to print that out. How many prime numbers are in V? Am I running out of time? I am. How many prime numbers are in V? This will just take a half a second here. So count primes returns an int. It takes a vector. It's a const vector of number. It's a passing a reference. And then we need to iterate through this thing. Almost done, just a half a sec here. But leave if you need to. So we range through there. And if V of I, the I number instance in V, if it's prime, then increment our count, and then return count. So I'm going to count how many primes are in that vector. Uh-oh. This is, I'm sorry to go over, really sorry about that. This is C standard live.
Will you need the seed or random also?
Just standard live? I think the C word. Let me try it. Is it standard live? C, I can't remember now.
Let's say that we misspelled return.
Oh, I misspelled return. Oh.
And don't you need the seed?
A seed?
Yeah.
Yeah, we do actually. Well, we don't need it, but we'll get a semi-random looking sequence. That's all right. So it's only 1,000 of these things, but the number is pretty big, so maybe it's going to take too long. Maybe we need to shrink this down a little bit. And this should be mod 200,000. I'll shrink that down a bit. So that doesn't make any sense, does it? You know what? I'm over. I'm sorry. I should not have continued. I'll finish this next time we meet on Wednesday. Oh, I didn't initialize count. See that? That's the problem right there. That's it. I didn't initialize count. 82. 82 out of 1,000 numbers. So what I wanted to talk about was the ratio. What's the probability that a number is prime? We're gonna estimate that probability.